Hi folks, Mr. Ackerman here. Thanks for watching. This is the supplementary video for Unit 5, Lesson 4. The topic is two-dimensional collisions and the law of conservation of momentum. So in G class you're going to find that there's the main video, which I hope you've watched by now. You're going to find the lecture notes, and you're also going to see a very short video that I've added showing a two-dimensional collision, which we're going to analyze in this video. And it's something we would have been doing if we were together in class. It's also something that you can do on your own at home if you have a flat surface and two marbles or ball bearings whose mass you are able to measure. Anyway, we'll get to that in a moment. So let's jump into the lecture notes and get started. So the first thing you're going to notice is this screenshot, which is from the PhET simulations. Now this might be one of the older PhET simulations. They sometimes update them. Sometimes you can get the older one, sometimes you got to go to the new one, but the idea is the same. And what I'd like to do is just jump into the simulation for a moment to show you how it works, and then we'll go through the math that you see written over here. So, whoops, we're going to be in Chrome and right over here. So the idea is if you click on the Advanced tab, you can set up a collision between two spheres, or pucks, whatever you want, on a frictionless surface. You can play around with their masses like this. I've set the masses equal just to keep things simple. And I've also clicked on some of the options that you see here. I want to see the momentum vector and the momentum diagram. Now I'm covering the momentum diagram right now, so I'm just going to move myself over a bit. There we go, that looks better. And you can see by clicking on this, you change the velocity of the ball, and you can do the same with this one. To keep things simple, I want this second ball to be stationary at the moment of collision, and it's also going to be a glancing collision, so like an edge-on collision that you might see in a game of billiards or pool. Now we don't really need the velocity vectors, so I'm going to unclick that so that we just see the momentum vectors. The reflecting border is this. It just keeps the ball in the frame, and it kind of makes you think of a billiard ball table, so I like having that. And the momentum diagram is down here, and you can zoom in and out. Anyway, I've slowed down the simulation speed so we can watch it and analyze it, but let's press play and see what happens. So the ball is coming in, and just pause for a moment. There is therefore momentum to the right, and the ball, the red one, number one, is going to strike the green one, and I think you can guess what was going to happen there. That was probably no surprise. The interesting thing is to look down here at the vectors in two dimensions, how they add up. And if you just rewind to where I was a moment ago, you'll see that this red line, which is the total momentum, it hasn't changed before and after the collision. The momenta of the individual objects has, but they add in a tip-to-tail way always to the original momentum of the system, which in this case is just ball number one. So, of course, this is a simulation, and it doesn't show you what would really happen, which is why we need to do an experiment. But before we get to the experiment, we're going to look over the mathematics of this. We're going to try a practice problem, and then we're going to do it. So let's jump back into the lecture notes. So the basic idea here, and once again I'm going to move myself out of the way. The basic idea here is that if momentum is conserved in the system, then it's conserved in all the dimensions. It's conserved in the x direction and the y direction. So really all we need to do here is think in terms of components, which you're used to doing. So I'm not going to spend a lot of time here. Everything's written out for you, and it's in the video as well. So the basic idea, as I said, we're going to look at components here. So we're going to be doing sines and cosines of various angles, but you need to be careful how you measure those. So to give you a better idea of how that looks in an actual calculation, let's go and take a look at a practice problem. And I need to move myself once more. So back down here I go. So this is question 4 on page 257 of the book. And again, because I didn't want to take time writing everything out, in real time I've got it written ahead of time for you, and you'll see this in your lecture notes. Diagrams are super important. We start with a before diagram. We have M1 incoming with velocity v1, M2 at rest with velocity v2, 0. Now it says in the question that the masses are equal, so we don't have to write m1 and m2, we can just write m, which I think you know is going to make things cancel out and make our lives easier. After the collision, you're given some information about the directions of the two objects, and now it's a little bit tricky here, so pay attention. It says after the collision, the velocities of the balls make angles of 31.1 degrees and 48.9 degrees relative to the original direction of motion of the moving ball. So the originally moving ball defines the x direction, just to keep things simple, and y is perpendicular. Now, every year I like to ask my students, when they give you these two angles, but they don't tell you whether it's above the horizontal or below the horizontal, how do you know that it's the way I drew it and not, instead of this, maybe something like this? How do you know it's not 31.1 and maybe 48.9 degrees like this? Because sometimes I get students who draw that, and I don't fault them for it until we take time to think about it. If you think about it, in the beginning here, all the momentum is in the x direction. There's no momentum in the y direction. Therefore, if the law of conservation of momentum applies, there can't be any momentum in the y direction after the collision. But if you draw both balls moving in the positive y as well as the positive x direction, then that means there is suddenly y components for both balls, which means the y momentum is not zero, and that violates the law of conservation of momentum. So we can't have what I just did there. They have to go in opposite directions. And if you think about it, going back to the simulation, if you've ever played a game of billiards, I want you to think about whether you've ever seen, let's reset this. Actually, I can just go back to the start there and pull this here. Could you ever imagine this red ball coming in, and after the bounce, the green ball goes up this way and the red ball also goes back up that way? It's impossible. And I'll give you a moment. Pause the video and think about the reason why. It's a very basic concept in this course. So have you had a chance to pause it and come back? If you guessed it's Newton's third law, you're absolutely right. The red ball pushes the green ball up and to the right here, and therefore the green ball pushes the red ball down and to the left. Now, the up and to the right push on the green ball makes it go up and to the right, because it wasn't moving before, so that's the only way it can go. The down and to the left equal an opposite push. How come that doesn't make this ball go left? Well, because it already had momentum going to the right, so it slowed down a bit in its rightness, but not completely reversing direction. Although I suppose you might be able to get something like that happening. You'll have to look at the individual situation and think about whether that's possible on your own. It'd be a good thinking question. Anyway, that's a classic problem. Because the math is fairly straightforward, I leave it to you to look through this, check in the textbook, if the solution manual, to see whether you're having any trouble, and message me if you are. But right now, what we're going to do is ask ourselves, is this stuff for real, or is it just mathematically what's supposed to happen? So, normally in class, what I do at this point is I have my students take out these soccer discs, which I think you've seen before. For those of you who haven't seen them for whatever reason, they're a little disc, maybe like 10 inches across, like a small pizza, and they take batteries, and there's a fan that blows, and it pushes air downwards so that they hover over the ground. And they're fun for kids to kick around because they move with no friction. So what I usually do in a nice big room, like maybe in the classroom or in the hallway, to turn these things on, and we do a two-dimensional collision like you just saw in the simulation. Unfortunately, where I'm recording right now in my house during COVID, I don't have a lot of room to actually do this, and so what I did was I went through my video library, and luckily I found a two-dimensional marble collision which I did on a level surface in school a few years back. And that is what is attached. If you go into G class, that's this one right here. So let's just jump in for a moment into, I have it open in iTunes, right over here. So let's watch this collision. It's filmed in slow motion, and the person holding the video camera is very steady, which is important for what we're about to do. And at the time, I had never done it before, and I thought, you know what, I'm going to put rulers on the x and y axes here so that people could make actual measurements. But really, it doesn't matter. You can make measurements using a ruler like this, just directly on your computer screen, or if you're using your phone, you can even use that. Everything scales linearly, up or down, depending on how big your screen is. So we really don't need those rulers that are in here, unless you want the actual number of centimeters the thing is moving. But it's filmed in slow motion anyway, so the time is not real. It's slowed down. And the only other thing you need to know is that these two ball bearings have equal mass. Okay, so let's click play and watch what's happening. So the initially moving ball is given a push, and you can see it goes in a line, just like the practice problem, which defines the x direction. And then there's a collision, and as expected, the balls go off on their own angles, like that. Now, what I could ask you to do is to take your phone and your stopwatch and make measurements from one point to the next, assuming constant velocity. And you could use a protractor to measure the angles that the balls go afterwards, and you could use a ruler to measure the distance. And with distance and time, you're going to have velocities, and with the protractor, you're going to have angles. And you can basically do the practice problem only in real life. However, since I'm such a nice guy, what I decided to do, took me a while, but I took a series of screenshots and I overlapped them so that you got to see the ball in stop motion at different points in the collision, and I measured the times, and here is what I came up with. If we were in class together, you'd be seeing this. So now this is not in the lecture notes, and therefore I'm going to leave it to you to look at this, pause this screen and take a look. And if I can remember, because it's kind of late at night right now, and I'm getting tired, but if I can remember, then what I'm going to do is I'll post a screenshot of this analysis. But let's take a look. You have the ball that is initially moving coming in, and I screenshotted it at 2 times. It looks a little faded because I had to adjust the opacity or the transparency of the layered photos so you could see one underneath the other. But what I did for you was I showed a line connecting the ball at one time and another time, and the times are 1.43 seconds apart. And by drawing a line between their centers, I can see the x direction. Now, I also measured on my computer screen 3.9 centimeters. You're using your phone, your tablet, your laptop, whatever. You have a different size screen, you're going to get a different distance here. So just take this for what it is. These are my measurements. But it tells me I went 3.9 centimeters in 1.43 seconds, and that's going to give me a velocity. M times that velocity is the initial momentum. Now ball number 2 is initially stationary, as you saw, and it went this way. You can barely see a very ghostly outline of the ball right over here. I measured off 5.2 centimeters at an angle of 31 degrees. And ball number 1 deflects up here. Again, you can barely see where it is, but just enough to measure 5.1 centimeters at an angle of 36 degrees. So what I did was I asked myself, is the momentum conserved in the x direction? And of course, I keep getting in the way here, so I'll move myself up. And let's see what we got in the x direction. Initially, as we said, m times the velocity, delta d over delta t. Now, I don't know what the mass is, so I just have to leave it as m. I only know that the masses of the two balls are identical. I remember that from school. So the answer I get is 2.7 to 2 sig figs times the mass. And that's all in the x direction. These are px total. Now, in the end, I've got to do a similar calculation, but with a cos 31 and a cos 36. And when I go through all that, you can check this out later, I get to 2 sig figs 2.5 m. So when I look at these two, I think, that's not bad. These two numbers are awfully close. I could say something like 2.5 out of 2.7 equals, and that's going to give me some percentage of momentum conserved. And you can see it's actually quite a bit. I think it's more than 90% of the momentum is conserved in the x direction. So I'm going to leave it to you guys as a student exercise for you to try what's going on in the y direction. Okay, so you're going to have this marble has a certain component in the y direction like that, and this marble has a certain component in the y direction like that. Of course, one of these is going to be positive and one of them is going to be negative. They should add up to 0 because there was no momentum in the y direction to begin with. Another way to look at it is instead of adding them and seeing how close you get to 0, just compare the two. Find this one, Py for object number 1, final, so prime, and find for this guy Py prime for object 2, and see how they compare. They should be equal. If they're not equal, how far off are they? Is one of them 90% of the other? Is one of them 95% of the other? Is one of them only 60% of the other? And that'll give you an idea of whether the momentum is conserved in the y direction. And so we're now going to finish off with one of my favorite questions in the course, and I hinted that there was going to be something about this back in a previous video. I can't remember if it was the the lesson 3 video or the lesson 2 video, but I told you there was going to be an interesting discovery. So before I can get to that, I have to introduce you to the question. It says here that a nucleus, now you all know what a nucleus is, initially at rest, fine, decays radioactively. What does that mean? Some of you know what radioactive decay is, and some of you may not. To remind you, to kind of get you thinking back, maybe at some point, I hope in your science education, you learned that some nuclei are not stable. They, for one reason or another, they have too much energy contained in them. And they can give off this energy in the form of what we call nuclear decay. Radioactivity is another word for it. And you may remember there's 3 basic kinds. There's alpha decay, there's beta decay, and there's gamma decay. In alpha decay, a nucleus actually breaks off some of its neutrons and protons, and they come flying out as a piece. It's actually 2 protons and 2 neutrons that come flying out, and that's a helium nucleus. So imagine a big nucleus like uranium, which is radioactive, literally spitting out an exact copy of a helium nucleus. It doesn't mean there's helium in the uranium. It means that the piece that broke off is identical to helium. And these are called alpha particles. You remember them from Rutherford's gold foil experiment, but that's not the one that this question is talking about. Skip beta for a moment. There's another one called gamma. In this one, it's not so much like a particle of neutrons and protons that goes flying out. It's actually a photon of very high energy, a gamma ray, and that's how the nucleus gets rid of some of its excess energy. So there's a difference between alpha and gamma decay. Alpha decay, you actually change the inner constituency of the nucleus. It loses protons and neutrons. It changes to another element. Transmutation is what that's called. But in gamma decay, that doesn't happen. It just loses some energy and it stays the same. Some elements decay by alpha processes and others decay by gamma. But the one that this question is about is beta decay. If we read a little bit, you'll start to get a hint of what's going on. It says the nucleus decays radioactively and it leaves behind a residual nucleus. So there's the big remaining chunk of nucleus left behind. But in the process, it emits 2 particles horizontally. An electron, and we tell you the momentum, it's going to the east, by the way, and a neutrino. We've heard about neutrinos when we studied dark matter, remember that? Neutrino with the momentum going south. So if I could just draw a little picture here of what's going on, it's almost like before we had this nucleus at rest. So there, not much to it, right? But then after, it's telling me that there is an electron going east, and I hope some of you just had a bit of a gasp. What is an electron doing in the nucleus? I thought electrons are in the shells around the nucleus. I learned that there's only protons and neutrons in a nucleus. So that's the first hint that something is weird here. And a neutrino going south. So here is south. Maybe I'll change the color there to keep these guys separate. Okay, so we've got, this is the neutrino, and this is the mysterious electron, which is not supposed to be living in the nucleus, but That's where we're going to be talking about beta decay in a moment. Now, question for you. If you think of this as an XY two-dimensional collision kind of thing, there's X, 0 momentum, and Y, 0 momentum before. The thing is at rest. Well, that means there's got to be 0 in the X and 0 in the Y after. But I look at this electron, and I see momentum in the positive X. So that's telling me there's got to be some balancing or offsetting momentum of something that's going this way, in the negative X. And similarly, for the neutrino that's going south, there's got to be something to balance that that's going north. Well, there aren't two things doing that. If there were two things doing that, this would be an easy problem. There's only one thing doing it. It is the residual nucleus. So the left behind bit of matter has an X and a Y component. And if we add these together, we get the final momentum of the nucleus. So you can think of this as the nucleus's Y prime or final momentum and the X prime or final momentum in the X direction, and these two add in a vector way to this. Now can you see how if something's at rest and then something goes east and something goes south, that leftover bit has to kind of go northwest? From the law of conservation of momentum, I hope you can see these three vectors, brown, blue, and pink, have to add up tip to tail to 0. So let's talk a little bit more about beta decay. This is the kind of radioactivity we call beta decay, and it's a little bit more complex than alpha. Alpha is simple. One thing, little helium nucleus goes one way, the residual nucleus goes the other. One-dimensional, done. But when scientists were studying certain elements back in the 1930s and even earlier, they found something strange, which was that when elements decayed through the beta process, you got an electron going one way, which is strange in itself, but they just thought the electron would go one way and the residual nucleus would go the other. But it didn't. It kind of went on an angle, and that's this angle right here. Why is it not 180 degrees the way you would expect if it was just an electron being spat out? And the answer was, but someone made the hypothesis, or many people did, that there must be some other particle. Now there wasn't a huge deviation in the angle from 180, so they knew that this particle that they hypothesized was not going to be very huge. It would be small. They called it a neutrino, which I believe in Italian means little neutral one, as opposed to neutron, which is neutral. Neutrino would be the little one. And you've heard from the dark matter lesson that we did, neutrinos are quite small. Well, knowing that momentum wasn't conserved properly, thinking of this as a one-dimensional collision, the hypothesis was made there's got to be another particle, and this led to the discovery of the neutrino. Now, I'm going to leave it to you guys to try to solve this question given the information here, because I think you can do it now. And again, if you get stuck, you can look in the solution manual or message me. But I want to just finish off by talking to you a little bit about this funny thing called beta decay. Why are electrons coming out of nuclei? You learned many, many times in your science education, they don't live there. So the answer is quite startling. We know that there's neutrons and there's protons in the nucleus. Well, imagine if I told you that sometimes these things can morph into other particles, just completely changing what they are. So for example, if a neutron were to suddenly change into a proton, well, that would be weird. You'd be going from something with 0 electrical charge to a +1 electrical charge, and that would violate the law of conservation of charge. So you'd have to imagine that there's some other particle, a mystery particle, which balances out this charge, has a -1. Well, guess what? It's not a mystery, it's the electron. And this is actually what happens in beta decay, more specifically, beta minus decay. In beta minus decay, A neutron in the nucleus of an unstable atom somehow decides to change into a proton, changing the type of element that you have in the process, because it's going to go up one on the periodic table, right? And also spitting out an electron. Now, all the laws that we are familiar with, law of conservation of energy, momentum, have to be obeyed. And so the one that applies to this lesson is conservation of momentum, and that's where the neutrino comes in. When it does this, it also spits out that little neutrino to conserve the momentum. And that is the story of how it was discovered. One last thing, interesting piece. We've talked a lot about fundamental forces. We talk all the time about gravity, and in the next unit we're going to talk about the electromagnetic force. We have a sense that the strong nuclear force plays an important role in holding nuclei together. But I told you at the beginning of our study of forces, we're not really going to talk much about the weak nuclear force. What the heck is the weak nuclear force? I understand the need for the strong nuclear force to hold together those protons that are repelling in the nucleus, along with the neutrons and everything. But what's the weak one? Well, guess what? The weak one is responsible for getting a neutron to change into a proton and an electron. So now you have a sense for the fourth fundamental force that we almost never talk about, and that is the end of today's lesson. So I hope you enjoyed that. I know it was a long one, but there's some cool stuff in there. Thanks for watching. Bye for now. Hope you're all staying safe. Take care.